So, good afternoon, all. Uh, in this lecture, we will discuss about map projections concepts and its application in remote sensing in GIS. I hope you in previous lecture you already know basics about the GIS. Uh, so, when we start an application in GIS, let's take an example. We need to construct some building, or we may take an example like police stations, a school. We have to construct in a city, in a vacant land, wherever the spaces are available, free lands are available. So there will be a certain criteria, like we are going to construct one school. A school should be somewhere in the some minimum density or medium density area. So you may get some childrens for your school. School nearby, any garbage land or dumping yard should not be there, so children should not be affected. School should not be far away from the main road, so it can be easily approachable. Vehicle can go there. Like that, we can have a different criteria we can fix, and we have to construct our school in the vacant land. Now, when we perform this analysis, we need information, all these information, which will be coming from the different sources. So you might be aware about the raster data and the vector data. In the previous lecture, based on the previous lecture information, you may be aware about that. So in that, like you need information of the road. So road information will come from where? It will come from the maybe from the road department or highway department. So they will give you in the form of either a digital form, it's a, like a road layers. They will give you like a vector layer in the form of, or they may provide you some sheet which you have to anyway digitize it. So that way the road layer information will come. Similarly, you will have an information of the medium density or lower density area. So that information basically coming from the your municipality. Similarly, like where is the garbage area, dumping area, wherever it is there, the water bodies information, forest information, these information may come from their respective departments. Now, there are two things. Why the first thing, this information, if it is in the digital form, that is either you may get in the form of raster layer or vector layer, then directly you can put in, bring into GIS environment, or we can it is a we can use in the GIS softwares. But if it is these are information now not in the maybe the digital form, you have to make it digitized first. So then so when this information will come from the different sources, they may have a different coordinate system or the projection system. So first thing, what we have to do, we have to digitize, we have to make a common coordinate systems or the projection systems for all the layers. Then only when we are performing such analysis, GIS analysis, it will be correct. If the one layer having a different coordinate system, another one is having a different coordinate system, analysis whatever you are going to do, it may not be correct or may not give the correct answers. So better make it in a uniform projection system or coordinate system, then only your analysis is going to be correct. So when you are if it is not there, you can easily transform from one to another. Second thing, like when we are getting this information in the form of paper sheet. Okay, so if what next is we have to digitize it.
Sorry,
Similarly,
sir.
if you have a
Am I
you
audible?
have yes,
Have you any slide for this lecture? Have you
uh,
any
pres-
slide for this lecture?
yes, slides are there, but first I am explaining the
That's
application of
most of.
application of only the
Most of
remote. I am only just telling first that's the application basically, and after that slides will move. Okay. So when next thing is that when you are having a basically what we can say that this paper sheet, you got information sources which does not have they don't give like digital form raster layer or vector layer. We have to use the basically paper sheet. Similarly, you have to compare the suppose the forest land cover maybe the 100 years back what was there and what is the present condition today. So whatever the information you are getting 100 years back, that was on definitely will be on the paper sheet. And today, whatever we are having it may be a satellite images. So that map, whatever existing 100 years back, you have to digitize it. And when you are digitizing and this after digitization, it will be like a raster data. So raster data, when you are bringing into the GIS software, QGIS or ArcGIS, then it will not have any projection system or coordinate system. But same time, you are having a you are comparing with this satellite images. So satellite images where already the coordinate systems and the projection system of the today's satellite image it is having, and one you have a scanned image. Now you want to compare both the things. So scanned image will not have any coordinate systems. So what you will do, you will assign the coordinate systems first to that particular image, and then only you will be able to compare. Correct? So this was another example. Similarly, you may have another, you are going to construct some new, what we can say, define your map actually. So when you are defining your map, you have to consider the curvature of the earth. If that curvature of the earth, if you may not be able to, what we can say, consider, then the whatever the map you are generating, which may match or it may not match with the existing maps. You already have seen in some of the maps in the basically corners they are writing like WGS 84 and LCC. Like these are the basically some polyconic. So these are the basically projection systems and the coordinate systems information. In that the map is basically defined. Generally in all maps, all thematic maps, they are basically writing scales, they are writing north arrow. This all the thing information will be there in that particular map. Okay, so that's why we will come to know in which projection system or coordinate system this map is there. And also whenever the satellite images are there also we are defining like as per our requirement, we can transform one projection system to another projection system. So in nutshell, if I say this is the primary and the basic requirement, and after that only we are proceeding for our GIS analysis. First, we have to define our projection system and the coordinate systems. Then only we are performing further proceeding for the GIS analysis. Now, we will start with our slides now. The basic stats about Earth, you know that so surface area is roughly 510.1 million square kilometer. Mass is around 5.9 into 10 to the power 24 kg. And its equatorial radius is 6378.137, and polar radius is basically 6356.752 kilometer. So you can see here the polar radius and the equatorial radius. There is some difference around 22 kilometer. It is difference we can see here. So both radius are not equal. If it had been equal both the radius, then we could have told that our Earth is like a perfectly sphere. But since both radius are not there equal, one is the equatorial radius, another one is the polar radius. Both radius are not equal because in a sphere generally or circle, what a circle case, a sphere case, what will happen? The radius will be equal. But here radius are different. So we have to define certain geometry for our Earth. We will come to that point. Flattening coefficient is around 0.0033528. It basically shows the basically flattening. Age is around 4.5 billion years, and elevation of land like with respect to the mean sea level, if we see Mount Everest, it is a 8848 meter with reference to the sea level, and it is comprises 7 tectonic plates, which are African, Antarctic, Australian, Eurasia, North American, Southern American, and the Pacific. So this is the basically picture from the space satellite image. Now you can see uh, our Earth looks like an sphere. As I just now I told you, it's not perfectly sphere because only 22 kilometer, because it's a 6,000 plus kilometer, and they are also not 6,000 plus. So only 22 kilometer difference is around there. Very minimum, we can say, with reference to the 6,000. So we are, it looks like a sphere, but it is not a perfectly sphere, first thing. Second things, what we can see, our Earth's surface is also not like a smooth surface. It is also somewhere mountains are there, somewhere trenches, valleys are there, somewhere plain area it is there. So Earth curvature is also not like a what we can say perfectly smooth surface. Hmm? So for surveying and mapping, most of the measurements we are taking on this Earth surface, and the surface of the Earth is an irregular surface. Directly using these measured values for further computation of distances, area, volume may not give the correct results. So because the irregular surface of the Earth is not mathematical. So first, what we have to do, we need such a surface which can closely defined, because it is an irregular surface. Now, what we want? We want such a surface which can closely represent our Earth. Okay, and that mathematical surface will be more useful for our estimation of area, volume, or whatever measurements, length, distances, whatever we are going to define. So we need such a mathematical surface which can closely define our Earth. So what is the basically that object or that surface will come? We need some modeling model of the Earth and all the measurements, and can then we reduce to that surface for the computation purpose. Once the model of the Earth is defined, so first we will define our model of the Earth. Then next thing is that to define the references point. References in the sense we need to define today I am telling I am sitting at a 78 degree point something 04 degree longitude. So reference is what? From where we are taking? We are taking as a Greenwich 0 degree as a reference point from where we are measuring, and I am sitting at a 78 degree 0.04 degree longitude. Okay, so that reference point. So similarly, distance from where, height from where, like mean sea level we are defining. So all the things we are some reference point we need to define. So first model we have to define, then reference points we have to define. So we need a coordinate system, reference system, datum for defining the position. We know that the Earth is not perfectly spherical, as I told you. So how to represent basically the shape of the Earth? The shape of the Earth can be best represented by an ellipsoid. Now, some of you may be aware about the ellipsoid, but still I will explain if those who are not aware will come to know. You know the circle, left side I have drawn a circle, and right side if you see there is an ellipse. In circle case, what will happen? If you see the distance from center to the circumference, it is called a radius, and it will remain same throughout the circumference. Now, double of this radius is called basically the diameter. So you take the vertical diameter, you know the diameter, double of the distance, double of the radius, and then you take the vertical diameter and just rotate this circle about its diameter. Okay, just rotate. And just imagine what's one three-dimensional geometry you are getting. That three-dimensional geometry is called basically an sphere. Okay, you assume that's a three-dimensional geometry will be then a sphere. Now you take the right side. What we have done, you just think like a circle. We have just pressed from top and bottom. Okay, just pressed. So it has come this way. that ellipse, this geometry is called basically an ellipse. So it is away from the circular position. Instead of this radius here in this ellipse, there will be a minor axis radius. Here will be a radius and diameter will be there in the circle, and ellipse case it will be a minor axis and the major axis. So how the complete double distance is called the minor axis, the vertical distance, and the horizontal distance, which is which is major axis. This is a, and that's the vertical distance, which is just reduced, is called the minor axis, and the horizontal distance, which is just expanded, it's called the major axis. Okay, and the half of the distance is called the basically semi major axis and semi minor axis. So there only the two terms were there in circle, radius and the diameter. But in ellipse case, there are the minor axis, major axis, and half of the distance minor axis is called the semi major minor axis, and half of the distance major axis is called the semi major axis. Okay. Now circle case, vertical diameter you have taken and just rotated this circle about its diameter. So three-dimensional geometry you are getting as an sphere. Now ellipse case you take this minor axis. You take this minor axis and rotate this ellipse about its minor axis. So the three-dimensional geometry which you are going to get is called an ellipsoid. So our Earth can be best represented by an ellipsoid. Okay, so this is not perfectly sphere. It's just basically difference, a minor difference. Ellipse can be of different sizes, but here in our case is the eccentricity is very small. So right down you can see the equation of this circle: x square plus y square equals to a square. X square upon a square, x square upon a square plus y square upon b square equals to 1. This will be an ellipse. So if a equals to b, that means a is a semi-major axis and b is a semi-minor axis. So if a equals to b, then what will happen? X square plus y square equals to a square. The minor axis will be equals to major axis. It will be nothing but the circle equations. Okay. So that way we are defining an ellipsoid. Now, an ellipsoid is the mathematical surface which can be generated by rotating an ellipse about its minor axis. Such ellipsoid is called an oblate ellipsoid. And our Earth can be best represented by this oblate ellipsoid. So when we are defining our ellipsoid, there are the certain parameters on which we define our ellipsoid, like semi-major axis, axis, as I defined in the previous slides, semi-major axis A, semi-minor axis B. Both things are clear. Now the third thing is the eccentricity. Eccentricity E square equals to A square minus B square divided by A square. A and B are the semi-major axis and semi-minor axis. Eccentricity basically shows that how much it is away from the circular position. If E is, you understand, if we press that circle little bit, then E value will be 0, near to 0, close to 0. If close to 0, and if we are pressing more, then E will be A will be more. Then again, that depends basically A equals to B. If A equals to B, then what will happen? A equals to B means like E will be 0. If E will be 0, A equals to B, when will be there? It will be a circle case. A equals to B is a circle case. Okay. So A equals to B is a circle case, and A equals to B, E will be 0. So in circle case, eccentricity will be 0. Correct. Now, if you are pressing less, that means there is a very less difference between the semi-major axis and the semi-minor axis between A and B. Okay. So that way, if you see the less difference, that means E will be value will be less. In our Earth case, only the difference is only the 22 kilometer in 6,000. So E value is less. If you are pressing more, That means there is a more difference between the semi-minor axis and the semi-major axis. So E will be value, E will be high. Okay, so that way basically eccentricity we define. Then flattening coefficient, it's just a ratio between the A minus B and the A, which shows the basically flattening coefficient. And if reference ellipse, so by using these parameters, we generally define our ellipsoid. A reference ellipsoid has its center a close approximation of center of mass of the Earth, and minor axis is parallel to the axis of rotation of the Earth. Latitude, longitude, and the ellipsoidal heights are defined on basically this reference ellipsoid. You see, this is our Earth curvature. By in red, you can see it's ups and downs are there. So we are fitting a one ellipsoid, one mathematical surface into this, which can closely represent our Earth. So this is a basically semi-minor axis and semi-major axis. And Earth case, we can say this is an equatorial radius. This is an polar radius. Now, these ellipsoids are also basically two types. One is a best fit ellipsoid and another one is a geocentric ellipsoid. Till now, we know that our Earth can be best represented by an ellipsoid. Now, these ellipsoids are also of two types. What happens in earlier time, that time we did not have a technology we are having it today, like GPS and VLBI, lunar laser ranging techniques. Different techniques are there which are available today. Satellite-based techniques, tracking techniques, which we have today, which we did not have maybe 100 or 200 years back. So that time also people did manual survey and use the local information, and they developed the ellipsoid. Since local information was used, or limited information was used, I will say limited information was used to develop these ellipsoids. So that ellipsoids, or based on that datums, the whatever they were more useful basically for the particular area only. This may not be suitable for the other side or other region of the Earth. For particular reason, it was more suitable. Other reason, it may not be suitable. That's why best fit ellipsoid. The ellipsoid is based on the measurement within a region, so it best fits that region only. Okay. The center of such reference ellipsoid does not coincide with the center of the gravity of Earth. An example of such ellipsoid is an Everest ellipsoid. So in India, we have also 1802 to 1839. We did one survey 1800 to 200 years back around, and then we developed one ellipsoid. So that time, some measurements were done from our Indian region, and based on that, ellipsoid was developed. That was more suitable for our particular region. But in today's time, when we are having a geocentric ellipsoid, means center will meet with the center of that ellipsoid will meet the center of the Earth. So we are having a now today WGS 84 and GRS 80 ellipsoid, which are basically developed in today's time, and globally we are basically using these ellipsoids. So if you see here, the geocentric ellipsoids, which are having like red, what we can say, it's basically almost matching with the Earth's surface, and the center of the geocentric ellipsoid, which will coincide, maybe be meeting with the Earth center of. Okay, and the center of best fit ellipsoid, the blue one, if you see, its right side, it may be suitable. Maybe the local information was used for this using this region for this region from this region. Then this blue one is suitable for this particular area. And if you see the left side, this side, it is far away, and center also it is far away from the center of the Earth. So that way we can say this is a basically best fit ellipsoid, may be suitable for a particular area. It may not be suitable for the other region. Okay, so that is a basically a best fit ellipsoid. And geocentric, which is globally it will be accepted, and the center will coincide with the center of the Earth. So when we developed this ellipsoid, that it was a result of great trigonometric survey carried out from 1802 to 1839. And here we use the conventional triangulational methods, which was best available technique at that time. And with that, if you see the Everest, whatever semi-major axis it is showing, 6377.301. And today, generally with the using the GRS 80, we are having a 6378.137. That means only some 800-meter difference it is there in the semi-major axis. That we did 200 years back, and that we got from the latest observations. So that means we did so precise estimation at the time 200 years back, which is closely matching with the 800 meters. Though it is today we are talking about the millimeter level accuracy. It is that way it is more, but still we can say that's without having any like GPS and maybe the best available techniques, which having a today, that time it was not there 200 years back, but still we did the good job, and the semi-major axis is closely matching, only 800-meter difference it is there. So you can say, so that Everest ellipsoid, whatever it was developed, it is also like a geocentric kind of things, because it is just only 800 meters in the semi-major axis difference it is there with the today's thing. So it is maybe the we can understand it's though it is a best fit ellipsoid, local information was used, but still it is a closely matching with the today's geocentric ellipsoid. This is the picture, basically the survey, the great trigonometrical survey that they did from Kanyakumari, the southernmost point of India, to the northernmost point of maybe up to Everest level. They have mapped the basically entire country in different segments, and then based on this information, they developed basically this ellipsoid. So once you generate your one ellipsoid, and then the next thing is that to basically to make it more real towards the basically it can closely represent our Earth. Means since it is an ellipsoid only, so we have to fix where should be the north, maybe the Earth's rotation axis. So this also we will fix. This is our Earth rotation axis. Okay. Where should be the like equator? Where should be our what we can say the reference point? X, Y, Z triode you have to fix in that ellipsoid. So X will be like a Greenwich meridian. Y will be the perpendicular to the Greenwich meridian, and it will be in the equatorial plane. Okay, the Z axis or the rotation of axis will be perpendicular from both the axes, X and Y. That means what we are doing, we are making it more real. So this is called an datum. Datum is basically depending on basically one ellipsoid. Ellipsoid is just a mathematical surface. From there, we are including the information into attaching the information onto this ellipsoid and making it more real, like a Earth, and called a datum. Okay, so today we are having a WGS 84, we are having a GRS 80, all geocentric ellipsoids or datums are available. Now, latitude, longitude, we can derive onto this datum or ellipsoid. Now, next thing comes to the like a geoid. So geoid is an equipotential surface level Earth's gravity field which best fit the mean sea level. So what happens when we are this ellipsoid we have derived. Now, next thing I'll show you, that's basically next in this ellipsoid we are deriving a latitude and the longitude. So how we derive, like suppose point P is there. From point P, we will draw a one perpendicular to the Earth surface. Okay, the blue line which is coming. Now this perpendicular, when we will draw it onto Earth surface, it will somewhere pass through the surface. And wherever it is passing through the surface, from there, one meridian will be passing. Okay, so this is called an observer's meridian. Like I am sitting here, and I just draw a perpendicular, it will go through the surface, somewhere it will go inside, and then the meridian which will pass from me, some meridian will be passing from here. Now, this angle between the Greenwich meridian in the and the observer's meridian, the angle between the Greenwich meridian, because already I have told you we have fixed this. This is our reference point. Okay. So reference point is we have a fixed, that's a Greenwich meridian, and the angle between the Greenwich meridian and the observer's meridian is called an longitude. Okay, similarly, the equatorial plane, and then from there, perpendicular angle, from there, the angle of the ellipsoidal normal. That's a normal, what the perpendicular you have basically drawn to the Earth surface. That angle between the equator and the ellipsoidal normal. This is basically called a latitude. And the perpendicular height from the surface of the earth to the point P, from the surface of the earth to the point P is called the ellipsoidal height, basically. Okay, so there are the latitude, longitude are basically for the horizontal information. Where are you, that we can find out. This is my position, latitude and longitude. The vertical information we can get from the different sources. The first thing is that the ellipsoidal height. You can measure your height with reference to the ellipsoid as well. Okay, in common, basically local or vertical in general. In general, we have seen that our height is basically from with reference to the mean sea level. So commonly everybody knows that thing. But height also can be measured from the ellipsoid as well. Okay, but the thing is that ellipsoid is a mathematical surface. It does not follow any gravity kind of things. But here in GIS or our regular practice, we are using the various applications which are maybe based on the gravity. So what we do, we develop or we define such a model, so which can be gravity based and which can provide height also. Okay, for horizontal means information where we are, that's a coordinate purpose, latitude, longitude purpose. This is fine, ellipsoid. But for height purpose, since it is not following the basically gravity based information, so we are going for some other reference point. Okay, what are the reference point? This is a basically geoid. So geoid is an equipotential surface where it's dealing with the basically gravitational potential energy. And what we do, there are the two things here, mean sea level and the geoid. So mean sea level we can understand like we are considering all the information of the sea level like high tides, low tide information, atmospheric effects, gravity, all the things, wind information, all the information we are gathering. Okay, and based on that, we are defining this is our mean sea level. It's not one day job. It's like a continuous observations they are taking, and if you take only the gravity based information, okay, the gravitational potential energy, then basically it becomes a geoid. So geoid and the mean sea level, the difference is very less. Okay, here geoid and mean sea level difference is very less. So in general, we are using the mean sea level information. We can use the geoid also for our height reference. Okay, and some of the places we are also using the ellipsoidal height also. Okay, but in our GIS analysis, basically we are taking reference as a from the mean sea level or geoid. Okay, and the difference between the both the height, geoidal height and this ellipsoidal height is called the basically, because definitely one height may say somewhere they will be equal also, somewhere they may be one will be high, another will place another will be high. Okay, so the difference will be there. So that difference is called the basically geoidal undulations. You can see here, and one height is small h, another height is capital S, and the difference between both the height is called the geoidal undulation. So latitude, the angle subtended at equatorial plane by ellipsoidal normal through the observer's point. Longitude, the angle between observer's meridian plane and Greenwich meridian plane. And ellipsoidal height, the height above the surface of the ellipsoid measured along the ellipsoidal normal. Okay, so this was basically about our dead term ellipsoid or coordinate systems. It was there. Now what we will do, using this three-dimensional geometry or the ellipsoid, what we got or datum. We will not be able to carry this three-dimensional things everywhere, or we need a more and more information about different themes. So what we will do based on this information, this three-dimensional map, we are going to generate different maps. Map is a basically two-dimensional thing. So from the conversion of here what we have three-dimensional thing. Here X, Y, and Z information is available. So the transformation of three-dimensional to the two-dimensional sheet or two-dimensional map is called basically a map projection. So here in three-dimensional, there will be three things: latitude, longitude, and altitude. But in two-dimensional, we will be having only the X and Y information, latitude and the longitude. So the transformation of three-dimensional space onto a two-dimensional map is called the map projection. A systematic arrangement of intersecting lines on a plane that represent and have a one-to-one correspondence to the meridian and parallels on the datum surface. So what we will use as like a three-dimensional geometry we have taken, and then we will put a one cone over there. Okay, and we will just project onto the wall of this cone. We unwrap this basically cone. So we will end up with a one two-dimensional sheet. Similarly, we may use the this one flat sheet already, which is a two-dimensional. We can put any part which wherever we want as per our requirement onto this globe. Then we project onto this flat sheet. So there will be a two-dimensional. Then we can use the another geometry like a cylinder. So we can put a cylinder inside that globe. Then we project onto the wall of this cylinder and then we unwrap it. So we will be end up with another two-dimensional map. So there are the geometries which are not flat but can be made flat. Means the two-dimensional map, that's a flat sheet, was not, the cone and the cylinder were not flat, but they can be made laid flat. Okay, after unwrapping it. So these geometries are also can be used for our map generation or projection. So when we are such surfaces are called basically the developing surfaces. The type of projections, when we are projecting generating these maps, certain things we need to keep in mind, like what exactly as per our different objective we can select a map projection, but when we are generating these map, there are the certain property which can be preserved and which certain properties cannot be preserved, like equal area projection. It maintains equal relative sizes used for maps that show distribution or other phenomena where showing area accurately is important. So some map projection will try to preserve the area in equal or relatively equal sizes. Similarly, the conformal, it maintains angular relationship and accurate shapes over small areas. So it will try to preserve the accurate shapes. So when you are projecting onto the two-dimensional sheet, the shape will not be that much, distortion will not be there. Equidistant maintains accurate distance from center of projection or along a line. So when you are projecting, that distance will be maintained. Similarly, the azimuthal or the zenithal, it maintains accurate directions basically. So these are the properties when we are projecting from three-dimensional to two-dimensional sheet and generating that one map, which maybe one map projection can preserve the one property, One map projection can may be possible that it may preserve the two properties, but it's difficult to preserve all the properties at a time. So different map will be generated. So as per our requirement, as per our objective, or as per our project requirement, we select such a map projection which may be more suitable for our objectives. Map projections can be classified based on their method of construction. There are many surfaces which are not plane, but which can be created by rolling a plane surface. Such surfaces are called the developing surfaces. Cylinder and cone are the surfaces. As an example, we have taken that's one cylinder or cone, and we will put one cylinder inside. Then we will project onto the wall of this cylinder, and then we will unwrap it. A map projection can be created by placing such surface on a globe, projecting the feature from globe to the surface, and then unwrapping the surface to make a plane. When we classify these projections, nature-wise, we can define as a plane, cone, cylinder, coincidence, tangent, secant, and superficial, and position-wise, normal, transverse, and oblique. So we know about the nature-wise plane, cone, and the cylinder. Okay. Now what we will do, we will go with the figure. You can see here that plane, cone, and cylinder. We are taking one example of one cylinder. So in this cylinder, now we have chosen such a cylinder where the radius is almost equal to the that ellipsoid or the dead whatever the three-dimensional figure object we are getting. Okay, so when this is equal, so the surface of the cylinder will just touch that ellipsoid or that. Okay, when it is just touching, what will happen wherever it is touching the boundary, wherever it is touching the surface of the cylinder. So when you will project, that line will exactly will come to the maybe the surface of in the two-dimensional map. Okay, so there will not be any distortion along the line. But when we are moving away from this line, the distortion will increase. Okay, so this is a basically first case is the tangent case where the both radius are equal. It is just a touch. Second case is the secant case. In that, if you see, there are the basically the cylinder is little small. Okay, the radius is little small. It is passing through the globe and it is coming to the others, coming from the other side. So it will cut at the two places. One from where it is going inside, another from where it is coming outside. Okay, so wherever it is touching, first and second place, there will not be any distortion along that line. And when we are moving away from this line, then the distortion will increase. Okay, then this was the normal case. Okay, though it was a tangent and secant, but the cylinder was in vertical position, normal case. Now you take cylinder and put it into the transverse case, horizontal. Okay, the figure you can see the transverse. Then you just insert that globe inside that cylinder. So again, the radius, if it is same, both plane, so it is a transverse case and tangent. Though it is a transverse, but it is also a tangent. Now, if you reduce the radius of this circle, it will pass at one point and come out from the other point. So there will be two places again. So this will be a secant. Okay, and oblique means a different angles if you are putting. So that is a basically an oblique case. This is an oblique case, but it is again a tangent case. Okay, because the radius, whatever you are taking, it is just touching. Okay. So first level differences you can find out normal, normal, transverse, oblique, plane, cone, cylinder. Then we have maybe the tangent case, secant case. Okay, and then after that also what we want to preserve. We want to preserve the area. We want to preserve the distances. We want to preserve the shapes. We want to preserve the directions. So Lot of combinations can be there. That's why different map projections, or maybe many map projections can be there from there. One ellipsoid you take and different projections you can get from that. Okay, but so when we are having a different projections, we need to select such a projection which may be more suitable for our objective. Maybe one person who those who is studying the entire country and the water study he is doing, another person is doing another different area, and maybe forest study he is doing, so he may select some different projection system, and the person first one is may select a different projection system. Okay, so that we need to select as per our objectives. Similarly, we have a conic projections, and we take one cone, we will put a cone inside that, and then we will project onto the wall of this, and then we unwrap it. So that's a basically conic projection. And in tangent, first when it is touching just surface, that is a tangent case, and then another one is basically the secant case. So these are wherever it is touching, there will not be any distortion. That line we are calling as a standard parallel. So in the wherever tangent case, there will be one standard parallel, and wherever it is a secant case, there will be two standard parallels. So many properties can be measured on the Earth's surface. Some of these properties are area, shape, directions, and distance. Map projections can be constructed to preserve one or some of these properties, though not all of them simultaneously. Each projection preserves or compromises or approximates basic metric properties in a different ways. The degree and the kind of distortion vary with the projection used. Some projections are suited for the mapping large areas that are mainly north and south in the extent, and other for the large areas which are having a more mainly east-west in extent. So based on the intrinsic property, we divide it into equidistant, conformal, equal area, and generation wise geometric, semi-geometric, mathematical, like that we can derive. So we can classify into different categories. Cylindrical, I will take some of the examples here. Cylindrical map projections, you can see here, we have put one globe inside that cylinder, and then we will we have projected onto the wall of this cylinder, and then we unwrapped it. So we will end up with a two-dimensional map. In cylindrical, there are the some few very well-known projections are there, Mercator and the transverse Mercator. If you see the Mercator projection, the Mercator is a basically cylindrical based on the cylinders. It's a cylindrical. So we understand like that cylinder we have put in the globe, we can put inside this cylinder, and then we have projected onto the wall of this cylinder. It's a basically basis cylinder. Conformal means like its shape will be preserved. Okay. Meridians are equally spaced straight lines. So meridians are basically longitudes. So these are basically equally spaced straight lines. When you are projecting, so some of the properties are there. So you can see in the figure, these are basically equally spaced straight lines. Parallels are unequally spaced straight lines. So parallel latitudes are basically unequally spaced straight lines. It is also can be seen here. Then scale is true along the equator. So as I was discussing, it is basically when it is a tangent case, then what will happen? It will just touching that line, the surface of the cylinder. When we will project onto this, so this line exactly will be coming to that. Okay, so there will not be any distortion. That means scale is true along the equator. When we are moving away from this line, the distortion will increase. So great distortion of area in the polar region, we can see here. So polar region, if you can see the cursor, this place is basically Greenland, and just compare the size of this Greenland with the India. Okay, Greenland is this much big, looks like it's an African continent itself, or half of the continent, because of the distortion, it is called. Okay, so that's why maybe more suitable for the navigation purpose we can use it. But wherever the area applications are important, we may not be able to use this. We may go for the some other map projections. Okay. So for a conic projection, the projection surface is cone shaped. Locations are projected onto the surface of the cone, which is then unwrapped and laid flat. In that one very well known projection, it is their Lambert conformal conic projection, LCC projection. Here it is a conical and conformal. Parallels are concentric arcs. Meridians are straight lines cutting parallels at right angles. Scale is true along two standard parallels normally or along just one. If it is a tangent case, then it is a one. If it is a secant case, there will be two. Okay, two standard parallels. So we can see here the picture. You can see here one standard parallel and there will be a two standard parallels. So this is the basically pictures you can see here. After projection, the parallels are concentric arcs. You can see here, and meridians are basically straight lines. So this is the basically LCC projections. It is more useful for the countries or areas which are having a more east-west expanses. Okay, then we have a another one is a polyconic projection. What we are doing, polyconic name itself, it's more than one cone we will use. Okay, conic, cone, poly means more. So more cone we will use. So this figure we can see, what we have done. We have here three different cones we have taken, red, blue and green. Okay, suppose we are of different sizes. So red cone we are putting onto the globe. Then wherever it is touching, I'm not taking the whole things. I will just take the strip, the very thin strip we will take. Okay, and I will know wherever it is touching, line will come exactly onto the maybe surface of the cone. Okay, there will not be distortion. It is a standard pattern. So that strip we will take and we will put it like that. Okay. Now we will take the another one cone which are having a different size. So it will touch at different places. Then we will take another strip wherever it is touching. So there will not be any distortion. That cone we will take. Then similarly the other cones we will take different sizes and then strip we will take and we will put like that. So we will take infinite small or very small strips, so which will be connected together and then the map will be generated. So this type of maps that we can see here, when the number of cones increases to infinity, each strip will be infinitely narrow and the result is a continuous polyconic projection. This projection will try to preserve the properties, all the properties. I will not say the 100% all, but definitely will try to preserve the properties, whatever we have discussed. Similarly, another one we have a universal polar stereographic UPS defined above 84 degrees and north latitude and below 80 degrees south. So it's basically like a flat sheet we will take where it will be more useful, either because flatness it is there on the north pole or the south pole. So we will use this type of projection system for north and south pole for better projection. Okay. Then another things we have a UTM projection where these are the basically large areas we have told that like different projections are there. Suppose some small area study we are doing, and so what we have done, we have defined the grids already, which are basically universal transverse Mercator UTM, particular case of basically transverse Mercator projection, and here we have derived the we define the grids of basically size is around 6 degree. Okay, of longitude wise, if you see longitude, we have defined 6 degree, and suppose anyone is falling in a particular zone only, then he will use the particular UTM zone number. So the idea is the distortion can be kept within a one region only. If we are not falling in that zone, then definitely we are going for the another zone. So we may not be affected with the previous zones, maybe the parameters. Okay, so for each particular zone, the different parameter, new parameters will be applicable. Okay, that way we can understand. So that particular zone is basically like suppose Dehradun, Uttarakhand is falling in the UTM 44 zone. So I will use any analysis if I am doing for a like a small area, whatever my study area it is there, I will select the UTM 44 zone. Okay, it is not affected by the UTM 44 things, 54, 45 things. So whenever another person, whosoever is using basically 45, may not be the new things he will be using for that different central meridian will be there, different things will be there. Okay, so that way basically grids are defined. So the error can be minimized within a particular grid itself. The choice of the map projection is made to give the most accurate possible representation, the geographic representation of geographic information, given that some distortion is inevitable. The choice depends on the locations, type, size, and the theme or the purpose of them. As I told you, we have a different combinations and different map projections available. We have a cone, we have a cylinder, we have a plane map, we have a in that also we have a tangent, we have a secant, we have a polysurface, polyconic projections, and in that also we can preserve the area, we can preserve the maybe the shape or other things, and that also we can in that apart from that we can put the cylinder in a horizontal way, you can put the cylinder in the vertical way. So a lot of combinations can be there, different map projections can be exist. So we need to select our one map projection based on the location, the shape, or the size or to be the of the region to be mapped, and the theme or the purpose of the map. The most important. As per our objective, we can select these map projections. And when we define after projections, we define certain parameter. Definitely, we should define these parameters because when we are generating a map, then somebody will use. So when the person will use, these parameters need to be defined. So when the person will use, he will be able to understand, okay, these are the parameters of this projections. Okay, accordingly, he can use in his application. To define the coordinate system completely, it is not sufficient simply to name the kind of projection used. It is also necessary to specify the projection parameters. It is important to know the projection and the projection parameter used in map imageries. Sometimes it is required to superimpose one map or image on another map. If map and imagery have different projection parameters, the details will not match if they are superimposed. The beginning, the first example when we are taking, that's a different from the layers will be having it from the layers will come from different sources. They may have a different projection parameters, and they when we are superimposing one to another may match or may not match if their projection parameters or the coordinate systems are not same. The set of parameters required depends on the kind of projection. So what are the parameters we need to define, like central meridian where of the projection for cylinder? The standard parallels, where the touch, as I told you, one secant case, tangent case, where there will be one or two respectively, the standard parallels will be there. The false easting, false northing, it's another concept which we define in projections. The units, whether we are having a what we can say meter, degree, in which units we are defining, and what after this projection, the reference ellipsoid. So this is from the one ellipsoid, all the things. Similarly, there are the different ellipsoids also there, but their map projections will be there. So that's why a lot of combinations can be there. So when we are generating a map, which is what reference ellipsoid was there, the three-dimensional geometry just previously we defined. So which was there, which we have used here. Okay, so all the parameters we need to define properly. So we need to project geospatial data for any analysis for different analysis like a school construction, police station construction, vacant land, or different analysis we are performing in the GIS. Make it possible to use data from the different sources. when we are performing these analysis, the data will definitely be coming from the different sources. Maybe it will maybe from the road department, maybe from the municipality, maybe from the forest department, water department. Different sources will be there. Okay, several projections to choose from. So different projection systems will be available. We need to select such a projection system which may be more suitable for our objectives and which can control the errors and which is basically more suitable for our objectives.